So the change in the maximum value or the value function f star will be roughly equal to now, these two derivatives can be found from the envelope theorem. So in order to find this derivative, we take the original function. Let me remind you, the original function was differentiate with respect to a and substitute x star, which was and the same for another derivative. So then it becomes and accordingly so then we're going back and we get and that concludes our solution. Now it's a proper time to get an introduction to the optimization theory with the constraints which are inequalities. The thing is that if we consider microeconomic problems, the majority of the problems, it's all about inequality constraints. Even for utility maximization problem, the budget constraint should be written as inequality in the form of utility should be maximized subject to constraint the price of x times x price of y no greater than the income, and also non-negativity constraints in almost all problems in micro. We have to account for non-negativity of the economic variables. So that tells us that we need to consider how to solve problems at least with one inequality. Here we have three. So let's consider a problem where there is a function of two variables and we would like to maximize it subject to just one inequality constraint. Both functions f and g are considered continuously differentiable, and we start with drawing. So we draw the coordinate plane, and that will be the graphical representation of the equation when we equate g and b. So below this graph, the set of xy coordinates satisfy inequality. Here g of xy is strictly less than b. Above the curve, g is strictly greater than b. As for the objective function f of x and y, we'll be considering the point where the level curve of f touches this constraint. This is a very similar picture to the one which was depicted earlier when we started considering optimization with equality constraints. The thing is that since we have inequality here, we should consider not only points which belong to the curve, but also the points which belong to the set under the curve. And that makes more cases to consider. Clearly we have the old case. Here, if the level curves provide the growth, so their depiction shows the growth of f in the direction of northeast, then here the gradient of f points exactly in this direction, northeast, and as for the gradient of g function, it points in the same direction. Now two gradients point in the same direction, so they're related. Gradient f is lambda gradient g, where g is necessarily a non-negative parameter. And we form Lagrangian function according to a concrete formula. So we follow the rule. Start with the objective function as before, choose plus sign, after that goes lambda, and within the square brackets we fill in with a difference, where we take the constraint, and for maximization problem we subtract from the bigger value the smaller value. That's how we get b minus gxy. Now, if we set the system of first order conditions, then we get immediately a similar equation relating gradient f and gradient g, because dl over dx is df over dx minus lambda dg over dx equals 0, and the same for dl over dy, the same. Now, how to consider additional case when we need to reconsider the picture. Maybe function f has maximum within this set. So if it does, so then these are the level curves of function f, and it takes the greatest value here at this point. So here, this point being x star, y star, we have df over dx equals 0, df over dy equals 0. What about lambda then? Lambda then should be 0 also, because actually we are considering an unconstrained maximization problem here. Both cases, when a maximum of f is taken at some point within the set g less than b, or on the boundary of the set at this point, it can be combined in one statement.